Okay, so I guess we can go ahead and get started. Oh, yeah, it always seems like my camera is like up here whenever I actually turn my camera on. Yeah, so hopefully everybody is doing well. I wanted to just give a couple of housekeeping things that I wanted to talk about before we start class. So we do have our homework assignment, as always, due this Friday. However, like I mentioned in my email, I am going to be away at a conference this Friday, so I will need to shift my typical Friday office hours to today, basically, from 5 to 7. I do realize it's a little bit of a later office hours schedule, but if you have any questions, yeah, feel free to drop by. If you're unavailable during those Thursday office hours, even though I won't be able to actually like meet, face to face, if you will, I will be relatively open to answering Piazza questions if you get stuck on anything. So yeah, that's what's coming up. What we're gonna do today is probably not finish, but get pretty close to finishing Unit 6, which is going to be all about how do we basically extend a lot of the existing clustering algorithms that we've talked about so far to be applicable to data sets that include categorical variables. So basically in this unit 6, we're breaking down our analysis into two types of data sets. So we're going to introduce algorithms that work for data sets that are purely categorical in nature, so purely categorical variables. And then we're also going to introduce algorithms that work for mixed data type data sets. So those kind of data sets that have a mixture of both numerical and categorical variables. Now, the cool thing about when we finish this unit is basically we'll have learned everything that we need in order for you to start looking at data sets that might be interesting to use in your final project. So basically your final project, we haven't talked too much about that, but essentially what it will entail is you picking a data set that is clusterable and yeah, basically applying a series of clustering algorithms that we've learned in this class to that data set to, yeah, basically detect any clusters that exist and learn more about them. So basically the main specification of this data set that you choose is that it should be clusterable. So specifically, when you plug this data set into the appropriate TSNE algorithm, you should see some evidence of a clustering structure. So if you have a data set that you find interesting that you'd like to learn more about via cluster analysis, basically after this unit, you can put it into a TSNE plot and determine if it would be a suitable data set for the project. Now I will be giving you backup data sets. You don't have to choose your own data set if you don't want to. So I usually supply 3 backup data sets as well, but something to just start thinking of, especially if you have like a particular data set or type of data set that you've enjoyed exploring in the past. Okay, so yeah, any questions on that? Okay, and yeah, hopefully the checking Tuesdays went well on Tuesday. If you ran into any, or as always, if you run into any issues with that checking Tuesday, you like while it's happening, you can reach out to Jordan. But if you had any, concerns about your submission, you can also reach out to me as well. So again, these checking Tuesdays, they're not meant to be this like serious, intimidating thing, if you will. So just wanted to keep that in mind. Okay, so any questions before we get started? Okay, cool. So where we left off on Tuesday was we talked about how to take our original TSNE algorithm and make one modification to that algorithm such that we can take a data set that is, comprised of, purely categorical variables or mixed, a mixture of categorical and numerical variables and basically get a series of TSNE plots, just like we do with the original algorithm, and interpret or be able to interpret those plots and determine aspects of the clustering structure of the original data set. So basically, the only modification that we made in this modified TSNE algorithm was that rather than using the Euclidean distance to measure the initial distance between 2 points in the original data set, like just purely numerical variables, we can rather supply our own pre-calculated distance matrix instead, and then basically use that to measure the initial distance between two original data set points, and then basically use that distance to find the TS&E distance in our similarity matrix P. So basically using that Gaussian curve as we do here. So for instance, if you had a data set that was purely categorical, you can use the Hamming distance matrix, because we know that the Hamming distance matrix can be used to measure the distance between pairs of points that are purely categorical. And then we can use that Hamming distance to find the distance between two observations in the original data set. Okay, so we had started working on that in our application. So again, we're looking at a bank data set. The rows are the clients at the bank, and our rows, or basically our attributes that we're currently looking at, have been turned into purely categorical variables. So even the age variable has been turned into a categorical variable as such. Now, in order to use the Hamming distance matrix, we actually had to label encode our categorical variable data set as such. Okay, so we put that label encoded categorical data set into a distance matrix using a function of the Hamming distance. So actually, this is not technically the Hamming distance between all pairs of points. It's actually the normalized Hamming distance, where we're simply basically taking the Hamming distance between 2 points and then dividing by the total number of attributes in the data set. So 10 here. So we want to analyze the clustering structure of this original categorical variable data set. So we use the same code that we've done before with the original TS&E algorithm, and we use the same procedure, more or less, for interpreting our resulting TS&E plots. So therefore, it's always a good idea to try out multiple perplexity values, starting at 5 and going to 50. And you want to remember, generally speaking, the researchers who have created these algorithms, have suggested that any perplexity values outside of that range tend not to yield as useful insights about your data set. Now, technically, we should also be examining multiple random states, but in the interest of time, we only are examining one here. This data set did take a little bit of time to run. Now, basically, the only difference between using a TS&E algorithm to detect the clustering structure for a categorical data set versus a numerical data set is that we have to supply our own pre-computed distance matrix. So our actual input here is the Hamming distance matrix that we had calculated above. Use a different color for that. Okay, and then we also need to specify that we are supplying our own pre-computed distance matrix here. So that's the only real modification here. So we can see that for the lower perplexity values, the TS&E plots, much like we would interpret in the original case, are not showing any evidence yet of any particular type of clustering structure. We don't see any gaps. However, as we move up in perplexity values, particularly as we're getting to the higher perplexity values, we start to see a similar pattern showing up for multiple perplexity values. And most likely, if you had tried out multiple random states, you would have seen a similar pattern showing up as well. So what we're seeing here for many of these perplexity values is the existence of perhaps 3 not super well separated main clusters. And then perhaps it could be the case, so we see some slight gaps showing up within each of these main clusters. So it might be the case that there also exist some subclusters within these main clusters that we have found. So based on what we see here across multiple TS&E plots, we can make the following assessment about the clustering structure of our original categorical variable data set. So these plots do suggest instance, that there is a clustering structure. And there might be three main clusters that are not well separated. These three main clusters are relatively balanced in size. So we see that more or less the same amount of observations are in this cluster, and this cluster. We do see some evidence of subclusters within some of the main clusters. Okay. Now, if we were looking at a TSNE plot that was generated with a numerical variable data set, there would be an additional element about the original clustering structure that we could interpret from those plots. So what is an additional interpretation that I have left out so far? So basically, if this was a TSNE plot generated with a numerical data set, what also might I say about the clustering structure? Or what aspect of the clustering structure could I further make suggestions about? Yeah, exactly. So talking about the shape. So if this was a so if this was a TSNE plot that was generated with a numerical data set, then I might start making suggestions about what the shape is. So for instance, in these scenarios, you want to be careful about examining the scale of the X and Y axes here. So actually, if the scale was the same, so basically if the scale went from -60 to 80 on both axes, we probably would actually see that these clusters are a little bit more smushed together. So therefore, they would be showcasing that these clusters here would be spherical. But, the question here is, does it make sense to say that a purely categorical variable data set has spherical clusters? Not so much. When we talk about cluster shapes in a data set, the implication is that we're dealing with like a numerical data set, if you will. It doesn't quite make sense to say that a cluster or a shape of observations in a categorical data set is spherical. So the interpretation that we're leaving out here in this particular scenario is the shapes. So it doesn't make sense to talk about cluster shapes in a categorical data set. So we leave that TSNE plot interpretation out. Okay. All right. Any questions on that? Okay. But basically, yeah, the interpretation of these TSNE plots, aside from the shape interpretation, is basically the same as what we've seen before. So for instance, what we would typically do at this point is we would select one of those perplexity value and random state values that best reflected what we observed across multiple random states and perplexity values. And then we basically use this final TSNE plot and TSNE coordinates as basically our representative of what the TSNE algorithm is suggesting about the clustering structure. And so, for instance, we could take this, finalized TSNE plot, and we can do what we've done in previous analyses. So we can, for instance, ask the question, what is the relationship between the clustering structure suggested by the TSNE plot and each of our individual attributes in the data set? So for instance, we can look at the relationship between the TSNE clustering structure and age. And we can see that for the most part, there's not really like a strong association between age and the clustering structure, right? Because more or less we see a roughly even distribution of all age ranges, within each of these three main TSNE plot clusters. But one sign or one evidence of some association, if you will, is that, for instance, we see that a lot of people that are, very much older do all tend to be put together in the same TSNE plot cluster. So basically, if you're looking to see if there's an association between a TSNE plot suggested clustering and, any particular other variable, you might ask yourselves the question, or you might ask yourself, how homogeneous, i.e. similar, are each of the TSNE plot suggested clusters with respect to the variable that you are color coding by. And then you might also further ask the question, to what extent are the values, i.e. colors, of this attribute all together in one, or just one, TSNE plot suggested cluster. So these can be helpful questions to ask yourself if you're ever trying to articulate whether or not there's, or, to what extent there's an association between a TSNE plot suggested set of clusters and any other attribute that you might be interested in. Okay, so for instance, we can also color code our TSNE plot by the jobs. And yeah, for the most part, we don't see a relatively strong association between job and the TSNE plot suggested clusters. But we do see that, for instance, the retired people all do tend to end up in the same TSNE plot suggested cluster. And this is actually, this makes sense here. We have a lot of old people and we have a lot of retired people here. So this, to some extent, suggests some association, but there's not really a strong association. However, for instance, if we move on to, some other attributes like education, we are starting to see somewhat of an association between education and not necessarily the main clusters that exist or are suggested by the TSNE plot, but perhaps some of the sub-clusters that the TSNE plot is suggesting. So you might say some evidence of an association between the subclusters and education. Okay. And this is because, for instance, these subclusters, or some of these subclusters that we're finding here, are completely homogeneous with respect to one and only one education level, for instance. Okay. And so basically, the question of whether or not they've defaulted on their loan, very weak association, or very, no association at all that we're seeing between any of the main clusters or the subclusters suggested by the TSNE plot. Same thing for the bank balance here. But we do see basically, for instance, the type of loan that they have, there is a strong association between, whether or not they have a housing loan and, the clustering structure suggested here. So this can all be some useful insights that you can extract from, any type of TSNE plot that you're creating here. So we haven't really explicitly talked about that. Okay. Any questions on that? Okay. So we talked about how to basically extend the basic or the original TSNE algorithm to incorporate or demonstrate the clustering structure of categorical data sets. Now, in addition, we'd also like to talk about how we might extend the k-means clustering algorithm, or basically modify the k-means clustering algorithm, such that we're able to create a single partition-based clustering of a purely categorical data set. So to do that, we're going to introduce or what we call the not the k-means clustering algorithm, but the k-modes clustering algorithm. And so basically the k-modes clustering algorithm is what we call a categorical analog of k-means. So we're going to see that the structure of k-modes is extremely similar to k-means, but the main things that we're going to be changing is what we represent the centroid with, as well as what distance metric we're using. Okay, so k-modes is going to be another prototype-based clustering algorithm that we're going to introduce. So whenever we're introducing a prototype-based clustering algorithm, you always want to think about, well, what is the prototype? So basically, what type of observation are we choosing to represent a given cluster? And what distance metric are we using? Okay, well, we're basically going to be using that same Lloyd's algorithm type of heuristic to help us solve a particular optimization problem. Okay, so much like in the k-means clustering algorithm, our input for the k-modes clustering algorithm is going to involve two things. So for k-means, our input is a set of m attributes where each attribute is numerical. And then we also need to include the number of clusters that we'd like for the algorithm to return. And then in k-modes, our input is the data set with m rows and n attributes where each of our attributes has to be categorical. And in addition, we also need to specify the number of clusters that we'd like to cluster our data set into. Okay. Now you want to remember the k-means clustering algorithm is actually a heuristic for the k-means optimization problem, right? So our overall k-means optimization problem is we want to find the optimal clustering of our data set such that the distance between each of our observations and the centroid of the cluster that they've been assigned to, i.e. the mean of the cluster they've been assigned to, is minimized. Now, in particular, the distance, so basically we're using the squared Euclidean distance in this optimization problem here. So it's not just any distance, it's the squared Euclidean. Okay, so the overall goal of the k-modes optimization problem is very similar. So again, what we're trying to do is we're trying to minimize the overall distance of each observation to the centroid of the cluster that it's been assigned to. But now one distinction is that rather than using the squared Euclidean distance in this optimization problem, we're now using the Hamming distance between each observation and the centroid of the cluster that it's been assigned to. Okay, so we now want to minimize the Hamming distance. Okay, and so, for instance, if we wanted to find, like, let's just say the Hamming distance between this observation here and this particular centroid, what would that Hamming distance be? Question for you all? So you want to remember the Hamming distance is not the number of agreements, it's the number of disagreements between each attribute. Yeah, exactly. So we see a disagreement here, and a disagreement here. So the Hamming distance in this case would be 3. Okay. All right. And so like I mentioned, the overall structure of the again, just like the k-means clustering optimization problem, the ability, so it's highly unlikely that we will ever be able to find a fast heuristic algorithm that can find the global minimum solution to this optimization problem here. So therefore, what we do instead, just like we did with k-means, is we use a heuristic clustering algorithm, which will hopefully find us a good enough clustering that gives us a hopefully low enough sum of the Hamming distance from each point to the particular centroid. So in other words, both of these heuristic clustering algorithms for k-means and k-modes offers us or is guaranteed to converge at a local minimum to the optimization problem that we're actually trying to technically solve. Right. So these two heuristic clustering algorithms operate in the very same way, right? So both algorithms, we have this centroid initialization step. And then what we do is we have this partition calculation step and this centroid calculation step. And then we keep iterating through these steps until a particular stopping criterion has been met. Okay, so in the first, or in k-means, our centroid initialization step is we randomly select k centroids. Now in k-means, usually what we did is we randomly selected a value between the minimum maximum value for each attribute in the data set. So basically we randomly selected observations using the uniform distribution between the minimum and maximum value for each attribute. And so given that we're dealing with a categorical data set, our centroid initialization step is going to have to be a little bit different. So one technique for randomly initializing your k centroids for k modes is to simply just find all distinct values for each of your categorical attributes and then randomly select values from each of these lists with replacements when randomly selecting your k initial centroids. So for instance, for the first centroid here, I might, let's just say, randomly select female from this list. That means female is, because we're drawing with replacement, female leaves the list. And so therefore the next centroid value would have to be male. Okay, and then let's just say, for instance, I randomly selected Democrat first from this list. And so the political party for the second centroid, because there's nothing left, would have to be independent. Okay, maybe I randomly selected PhD for the highest education level for centroid 1. And then I would have to select masters. There's only 2 values here. And let's just say, yeah, and so on and so forth. So let's just say I randomly selected apartment for the type of home for centroid 1. And let's just say I randomly selected house, or I would have to select house for the type of home for centroid 2. Okay, so I've initialized or randomly initialized my first k centroids here. Okay, and so actually, let's skip over to the partition calculation step. So basically, after you have initialized your first centroids, then you are going to create your first clustering. So much like in k-means, where our partition calculation step involved assigning each observation to its closest centroid, we are going to assign each observation in the k-modes clustering algorithm also to its closest centroid. We want to be careful about the distance metric that we're using here. So when we say closest in k-means, again, we want to remember that we're using, the distance metric that we're using is the squared Euclidean distance metric. Okay, between the observation and the centroid. But in k-modes, we are now using the Hamming distance between a given observation and its centroid. Okay, so for instance, actually, I think I can do a poll for this one. So which of these two centroids would we assign object 3 to? Okay, so try to submit in the next few seconds. Okay, so maybe I asked a very softball question here. Yeah, so first you would calculate the Hamming distance between observation 3 and centroid 1. So there are, let's see, just one disagreement between centroid 1 and object 3. So that would be the Hamming distance between those 2 points. And the distance, or the Hamming distance between object 3 and centroid 2 would be 3, because there are 3 attribute disagreements between those 2 observations. So therefore, in the partition update step, you would assign observation 3 to centroid. All right. And so we have our partition update step, just like we do in k-means. And then we also have our centroid calculation step, just like we do in k-means. So in the centroid calculation step in k-means, we want to remember that our centroid is represented as the mean of the cluster. So basically, we recalculate our k-means centroids by taking or calculating the mean of that given cluster. However, the reason why k-modes is called k-modes is because the way that we calculate the centroid of a given cluster is that we calculate the mode of each of the attributes in the given cluster. Okay, and you want to remember the mode of a cluster, or the mode of a the categorical variable is the attribute that appears most frequently. Okay. So, let's just say this was our cluster here, and we wanted to recalculate the centroid of this cluster. So what would be the gender of this centroid? All right, am I making this too easy? Yeah. Male. And what about political party? Yeah, independent. Yep, independent. And highest education level would be master's. And type of home, thanks guys, would be house. That would be our new centroid for this particular cluster. So we would do this for all clusters, just like we do in k-means. Okay, so what we do is we keep iterating through the partition update step and the centroid update step until our particular stopping criterion has been met. So just like we saw in k-means, we stop the algorithm if the centroids from the previous iteration are the same as the centroids from the current iteration. And so the stopping criterion for k-modes is going to be the same. Okay. All right. Any questions on that? Okay, cool. So just to recap, at this point, now we have talked about 4 prototype-based clustering algorithms. And so like I mentioned, the way to distinguish, the way to disambiguate between all of the different prototype-based clustering algorithms is you want to ask yourself what prototype, i.e. representative of a given cluster, are you using? And then what distance metric are you using? But then other than that, the structure of each of these algorithms is exactly the same. And then on top of that, each of these clustering algorithms, if we use the prototype and distance metric that we're supposed to, are guaranteed to converge to the local minimum of the optimization problem that we are trying to solve. So just to recap, what is the prototype of k-means? I'm asking very basic questions here. The mean, right? And then just make sure we're all on the same page. What distance metric are we using for k-means? Right. Okay. Not the Euclidean. You're close with Euclidean. Yeah, exactly. We want to make sure that we're using the squared Euclidean distance metric. Otherwise, the k-means clustering algorithm is not guaranteed to converge to the local inertia minimum. Okay. And so as a recap, what is the prototype that we use to represent a cluster in the k-medoids algorithm? Maybe this is a basic question. Now here's a more nuanced question. So what distance metric are we using for k-medoids? Anybody remember? So if I said Manhattan distance, would that be wrong? No. If I said cosine similarity, would that be wrong? So the distance metric, the cool thing about k-medoids, right, is that can be any distance metric you want. Right, so the cool thing about k-medoids is that you can use any distance metric that you want, and the algorithm is guaranteed to still converge to the local minimum of the optimization problem that you're trying to solve. Okay, so let's just quickly go through the rest here. So k-medoids, excuse me, k-medians, the prototype is the median. And the distance metric that we need to use is the Manhattan distance, i.e. the L1 norm. Okay, and we just introduced a new prototype-based clustering algorithm. So we have k-modes, where the prototype is the mode, and the distance metric that we need to use is the Hamming distance. Okay, and I'll just say we need to use these specific distance metrics. Otherwise, the algorithm is not guaranteed to converge to the local minimum, or to a local minimum, excuse me, of the corresponding optimization problem. Okay, you want to keep this in mind. Any questions on that? All right, cool. So let's take our k-modes clustering algorithm and let's apply that to our bank client data set. Okay, so in order to use k-modes, so unfortunately k-modes is not a clustering algorithm that the scikit-learn package contains. So you will need to install an additional package for that. So basically you just need to run pip install k-modes. Just written that down. Okay, and so once you install that package, the nice thing about the k-modes function is that it very much has the same structure that the k-means function has from scikit-learn. So for instance, let's just say we wanted to perform a naive clustering of our categorical data set. So simply just looking for two clusters that we weren't really informed about. So we can specify the number of clusters that we want. And because, as you might have noticed, as with all of these prototype-based clustering algorithms, these are k-modes is a non-deterministic algorithm because we randomly initialized our k-centroids. So we should fix a random state. And at this point, we have yet to actually fit or basically implement our actual data set. So what we've essentially just done here, and we can do it this way if we'd like to as well. And for instance, when using scikit-learn or any or basically any scikit-learn function, is we can take that k-modes object, which we've just created, and then apply, for instance, the fit predict function with our categorical variable data set that we've label encoded. And again, what the fit predict function does, it actually does two things. So the fit actually runs the algorithm, whatever algorithm it is that we're referring to. And then the predict or the transform, we have fit predict and we have fit transform. They usually do the same thing in a lot of cases. What that will do is basically return some sort of pertinent output, if you will. Okay. So the fit, so basically the fit predict returns the actual cluster labels for the given data set. That's this here. But once we've run the fit or fit predict or fit transform on a given scikit-learn or object that comes from a package that mimics scikit-learn, like this one here, we can extract all sorts of other information about the clustering as well. So for instance, we can extract our cluster centroids, much like we do with k-means. We can also extract, using the cost attribute, the objective function value that we were trying to minimize. So for instance, in our case, this cost attribute represents the Hamming distance, sum of the Hamming distances of all observations to their respective cluster centroid. Okay, so basically this is the thing that we're trying to minimize when running the k-modes clustering algorithm. Okay. However, this was just a naive implementation of k-modes. We really have no sense as to how many inherent clusters actually exist in this categorical data set. So, much like we've seen with our other prototype-based clustering algorithms, one way that we can go about determining how many inherent clusters exist in the data set is we can create a k-modes elbow plot. So, much like we did when creating a k-means elbow plot, we can cluster the data set using k-modes a certain number of times. So let's just say I've decided to cluster the data set with k-modes, asking for one cluster. So let's just say I do it 3 times. And so what I would do is I would find the sum of the Hamming distances of each of these 3 clusterings, each with 1 cluster each. And then I would calculate the average sum of those Hamming distances and put that on the y-axis here. Okay, and so I would do that asking for, for instance, 2 clusters from k-modes, 3 clusters from k-modes, so on and so forth. Okay, and the way that I interpret the k-modes elbow plot is very much the same as how I would interpret any kind of elbow plot that we've talked about in the past. So basically, in these elbow plots, we're looking for a dramatic elbow, right? And so the more dramatic of an elbow does not necessarily mean, or basically if you don't see an elbow, right, that doesn't necessarily mean that the data set is not clusterable. It's more that the particular algorithm that we're using has failed to detect a strong clustering structure. So basically, the more dramatic of an elbow that you see, what that means is that k-modes is detecting or is able to a clustering structure in the data set. Right? And then also, like in the k-means elbow plot, you know, a indication as to perhaps how many inherent clusters might exist in the given data set that, you know, the given algorithm is at least able to detect, is where you end up seeing the curve leveling off. So now this is actually interesting here. So we can actually see 2 points of leveling off here in this k-modes elbow plot. So what we might do, so it might be a good idea to inspect a k-modes clustering, asking for both k equals 2 clusters as well as k equals 6 clusters. Okay, so maybe this might be an indication that k-modes is detecting perhaps a, you know, 2 main clusters, and then perhaps those 2 main clusters perhaps might break down further into, you know, perhaps 6 subclusters. So that could be one interpretation of this. Okay. Any questions on that? Okay, so we can apply we can create a k-modes elbow plot using very much the same code that we've done when creating the k-means elbow plot. Some of the key distinctions here would be, so for instance, you would want to, rather than extract the inertia of your clusterings, you would want to extract the cost, i.e. the Hamming distance of all points to their cluster centroids. So here we're using our k-modes function, asking for a series of cluster numbers going from 1 to 9. Okay, and so this is the elbow plot that we end up getting here. Okay, so let's choose to focus on this first leveling off, if you will, but a more complete analysis would also choose to focus on 6 clusters as well to see if you can find some additional hidden insights. Okay, so one more time, we're going to cluster the data set using k-modes, looking for 2 clusters. Okay. I'm going to use fit predict on my label encoded data set to create my cluster label. So I'm going to put this or create like a new column in my original data frame. Okay. And then what I could do is if I'd like to get some additional corroboration, for instance, that my 2 k-modes clusters actually have meaningful separation. So there actually exists. So ideally speaking, in, you know, let's just say in my particular analysis, you know, again, it would be great for me to not just take a blob of points and simply just cut them up into, you know, 2 clusters, if you will. Ideally, there should be some sort of meaningful separation that exists between the clusters in this categorical data set. So again, like we've seen when using k-means or many of our other numerical attribute clustering algorithms, we can use the corresponding TSNE plot to help provide additional corroboration that there might actually exist some meaningful separation between the k-modes clusters that you know, that k-modes has identified. So for instance, we can color code our Hamming distance TSNE plot with our k-modes cluster labels, as we've done here. And so let's see how we might interpret this here. So, no. So we want to think about how much association are we seeing between the TSNE plot suggested clusters and our 2 k-modes clusters. So try to submit in the next few seconds. Okay. So we're seeing somewhat agreement or very little agreement. So to some extent, we're kind of setting ourselves up for failure, if you will, if we expect to see, complete perfect agreement amongst the three, main TS&E plot suggested clusters that we can see, and the two K-modes clusters that we're finding here. But we can see some existence of an agreement or an association between these two sets of suggested clusters, right? Because we can see, for instance, that, this TS&E plot suggested cluster here is mostly homogeneous with respect to cluster 0. And then this cluster here also is mostly homogeneous with respect to K-modes cluster 0. And this cluster here is relatively homogeneous. Well, actually, so this cluster here is, it's actually not very homogeneous with respect to the two K-modes clusters here. But what we do see, though, is that K-modes cluster 1 relatively tends to be all together within the same TS&E plot suggested cluster here. So all of these elements that we just mentioned suggest that there is some agreement that exists between the K-modes clusters as well as the TS&E plot suggested clusters. So this could give us some sort of an indication, for instance, that there exists some meaningful separation between most of the observations in K-modes clusters 0 and 1. Okay, so for instance, we can see that most of our K-modes cluster 1 values do end up being separated from most of our K-modes cluster 0 values. Okay. So someone's asking if a TS&E plot has a small cluster of blue points concentrated in a certain area and another plot has the same points scattered, what would the differences suggest? Yeah, that's interesting. So that would suggest some sort of so it's, basically a complete lack of association is if you have all of your colors, if you will, completely evenly distributed amongst, the however many TS&E plot clusters that you see. So what that could be an indication is that, whatever differences that the TS&E plot is finding seems to have some sort of an agreement with, let's rephrase this. So the similarities that the TS&E plot is focusing upon when it creates the projection is the same set of similarities that K-modes is focusing on when it creates its clusters, at the very least for that, small little set of observations that was within one of those clusters. So that would be an interesting insight to witness. And so you might, if you saw something like that, you might, focus on that particular set of observations and see, well, what makes that particular set of observations distinct from like the other observations that were more evenly distributed amongst the other TS&E plot clusters. So most likely you would find some sort of interesting pattern that suggested perhaps some sort of a subcluster relationship, if you will, amongst, for instance, the K-modes cluster 1 that you identified here. So basically it would open the door to extracting more interesting insights about, what your data set is actually telling you, basically. Okay. Cool. That's a good question. So we can see that, to some extent, we set ourselves up for failure if we wanted to truly examine if we could find a modes clustering that had, a perfect association with the TS&E plot suggested clustering, because TS&E plot suggested that there's 3 main clusters and we were only looking for 2 K-modes clusters. So to be thorough, we might take our suggestions based on the TSNE plot, that there's 3 inherent clusters in the data set, and we might decide to look for 3 clusters with K modes. Okay, so we find those new cluster labels, and then we color code those new cluster labels in our TSNE plot again. Okay, and so basically what we're seeing here is that by allowing for 3 K modes cluster labels, we didn't really see any additional association showing up between what we see with the TSNE plot and what we see suggested by K modes, right? So for the most part, we still see that this cluster here is relatively homogeneous with respect to K modes cluster 0. And for the most part, we still see the same thing happening with this cluster here. But what we see here is a further splitting up of this TSNE plot suggested cluster here. So this is still a relatively diverse cluster with respect to the 3 K modes cluster label. So basically by including a 3rd cluster, we didn't get any further corroboration, at least from the TSNE plot, that this 3rd cluster that we had introduced was going to bring any more meaningful separations of the data set, basically. Okay, so we might instead choose to just focus on the K modes clustering with 2 clusters, because that was what the TSNE, or excuse me, the l12 plot at the very least was suggesting about how many clusters it was able to identify. So we might instead choose to focus on the insights that K modes with 2 clusters basically shows us. So to learn a little bit more about categorical dataset clusters, we can use similar analyses for what we might have done with K-means clusterings. So for instance, we might choose to examine the centroids of each of our 2 clusters that we found. And then we might also choose to examine the relationship that exists between each of our categorical variables, one at a time, and our cluster labels. So if we want to extract our cluster centroids, then unfortunately, those cluster centroids by themselves are not super insightful, right? Because they're still label encoded, which is something that we had to do in order to run the K modes clustering algorithm. So luckily, when we created the encoding of our categorical variable data set in the first place, we want to remember that we kept the label encoder object that corresponded to each column from our original data set. So in other words, we created this dictionary that we called label encoder, where each of the keys of the dictionary corresponded to the label encoder object. And basically that label encoder object now contains the mapping that exists between the labels for that given column and the actual categorical variable value that it corresponds to. So if we wanted to unencode our resulting cluster centroids, what we could do is first create a new data frame, which is basically just a copy of our encoded centroids data frame. Okay. And what we're going to do, just like when we encoded our original data set, we're going to iterate through each of the columns, each of the column names in that data frame. And then what we're going to do is we're going to reference the label encoder object that corresponds to that given column name that we're considering, so job, for instance. And then our label encoder object, it has a transform function, which basically takes a given set of categorical variable values or string values and converts them into numerical labels. And then conversely, the inverse transform function will take a set of label encoded numbers and map them back to the corresponding categorical variable values in the map. So for instance, the label encoder for job remembers that a 1 translates to blue collar, essentially. So what we do is we're going to basically create a new column in my df centroids data frame that corresponds to job, and it's going to have unencoded this column here. Okay, so on and so forth. So we basically unencode each of our centroid values here. Okay, so we can examine the centroids here. So we can see that, for instance, the most common job for people in centroid, or the most common job for people assigned to cluster 0 are people who are blue collar. The most common marital status is that they're married. Most common education level is secondary. Okay. Conversely, the people assigned to cluster 1, their most common characteristics are people who work in management, people who are single, people who have a tertiary degree. So simply just based on this set of centroids alone, I might be perhaps picking up on some sort of socioeconomic status division here, perhaps. Okay, so I'm simply just looking at the most popular attributes. So the centroids in K-modes, much like the centroids in K-means, they're simply just based on a single set of summary statistics. So it's just a single metric. So if we wanted to learn more about what types of attributes characterize a given set of cluster labels, we can look at the relationship that exists between, like I said, each attribute and our cluster labels that we found. So you want to remember each of our attributes are categorical, right? And our cluster labels are also, we can also think of them as a categorical variable. So if we ever want to, evaluate the association that exists between two categorical variables, one way that we can go about doing that is by first creating a cross tabulation, basically, of every single combination of, let's just say, one of our attributes like job and our predicted cluster labels 0, 1. So if we wanted to do that in Python, we can use the cross tab function. Okay. And we can look at the relationship, or so we can cross tabulate the relationship between our job attribute and our predicted cluster column in the df cat data frame that we've created. Okay, and then I might also choose to normalize these counts over the index. So in other words, what I've just created here is a cross tabulation table, for instance, which shows me that the percentage of blue collar workers that end up in cluster 0 is 97%. And the percentage of blue collar workers that end up in cluster 1 is about 3%. Okay, so if I wanted to create we call a side-by-side bar plot visualization, visualizing each of those sets of percentages, I can create this bar plot like such, right? And so what this bar plot is further indicating to me is that there is actually this socioeconomic status breakdown going on between the two clusters. So for instance, I can see that the blue collar workers, like a very high proportion of blue collar workers end up in cluster 0. On the other hand, a much higher proportion of management workers end up in cluster 1. Okay, so this is one way to go about looking at the association, or basically what types of attributes, or for instance, how the job attribute might relate to the cluster labels. So in this case, basically, we were breaking down the percent, or basically what percent of a given job corresponded to each cluster. And this is because we basically put the job column first. But we could have switched up the order of the predicted cluster and the job attribute to get a slightly different analysis. So for instance, by simply just switching up the order here, so by putting the predicted cluster first and then the job second, what I end up seeing here, for instance, is the percentage of people assigned to cluster 0 that belong to each of these 10 or however many job types. So furthermore, I can keep seeing the socioeconomic status breakdown, for instance, where like the most common job for cluster 0 is blue collar, and the most common job for cluster 1 is people who work in management. Okay. So furthermore, if I wanted to, for instance, perform a complete or more thorough analysis, I would do this for every attribute in the data set. So for instance, I would look at the relationship between education and predicted cluster. So for instance, I can see that people with tertiary degrees are much more likely to end up in cluster 1 than people with lower degrees, whereas people with primary and secondary degrees are much more likely to end up in cluster 0 than those with tertiary degrees. So we further see this, socioeconomic status breakdown. And so this is where I was putting education first and predicted cluster second. So alternatively, I could have also switched up the ordering as well to get a slightly different analysis. And so I can see this association here as well, where, for instance, cluster 0 or cluster 1, let's just say, is highly comprised of people with tertiary degrees, much more than cluster 0. Whereas cluster 0 is much more comprised of people with secondary degrees, more so than those in cluster 1. Okay. All right. So this is how you would examine for instance, what attributes characterize each cluster in a single partition-based clustering. Okay. All right, questions on that? Okay, so really quick, the final type of clustering algorithm that I wanted to introduce that we've seen before, but now basically based on a couple of modifications, we can also apply to purely categorical data sets. So that additional clustering algorithm that I'd like to talk about is how we might take our agglomerative hierarchical clustering algorithms that we were using for numerical data sets in the past, and how we might apply these same techniques for data sets that are, for instance, purely categorical. So in the past, when we introduced hierarchical agglomerative clustering algorithms, we specified that each of our attributes in our original data set should be numerical. And the reason why is because one of the steps, or basically the first step in each of our agglomerative hierarchical clustering algorithms, was we took our original data set and we created a distance matrix. And so that distance matrix, that first distance matrix that we created, was our first proximity matrix that measured the distance between each of our singleton clusters. And so, we didn't really specify otherwise, but the implication or the implicit distance metric that we were using to originally measure the distance between all pairs of points, i.e. all pairs of singleton clusters, was simply just the Euclidean distance metric. Okay? And so the thing here is we didn't actually need to use the Euclidean distance metric as our original proximity matrix. We could have used any distance or any sensible distance metric that we wanted to. So for instance, if you want to create a hierarchical cluster, or if you want to run a hierarchical agglomerative clustering algorithm on, let's just say, a categorical data set, then rather than using a original Euclidean distance matrix, then you can use a distance matrix that is more well suited for measuring the distance between pairs of points in that data set. So instead, maybe I might use a Hamming distance instead. And so by being flexible about the type of distance matrix that you use in your initial step of the hierarchical agglomerative clustering algorithm, the observations that you're clustering can be any data type you want. So for instance, it can be numerical. Your data set can be purely categorical, or it can be mixed data types as well. Okay, but basically once you supply that original or that initial distance matrix or proximity matrix between each set of observations in your original data set, the hierarchical agglomerative clustering algorithm works in exactly the same way. So we keep using this original distance matrix to, for instance, find the two closest clusters. So in this case, it would be 0 and 4. And then we merge 0 and 4 and create a new proximity matrix. And then we would use, single linkage, average linkage, or complete linkage to basically measure the distance between the two, or between the new sets of clusters that we're dealing with. Okay, so for instance, single linkage is still the distance between the two closest clusters that we're dealing with. But now the distance, or excuse me, single linkage is still the distance between the two closest points in two clusters. But that distance metric that we're using now is, in this case, it would be the Hamming distance between those 2 points, as opposed to the Euclidean distance. Okay, but the general algorithm is the same. Okay, any questions on that? Okay, so let's implement this on our categorical data set. Okay. So, all right, so basically the way that we implement or create a dendrogram starting with a categorical data set is basically going to be exactly the same as how we did it when we were starting with a numerical data set. Really, the only difference is we are now specifying that our initial distance matrix should use the Hamming distance as opposed to the Euclidean distance. Okay, but then everything else is the same. So we have our initial distance matrix that we create with the pdist function here. Okay, now keep in mind the input for our clustering algorithms is so the distance matrix input for our TSNE function versus our hierarchical agglomerative clustering functions are going to be slightly different. So when creating a dendrogram in hierarchical agglomerative clustering, the distance matrix has to be created with this pdist function, which gives us this flattened distance matrix. On the other hand, if we wanted to take that flattened distance matrix and put it into square form, you can use that square form function here. So what you want to remember is that the TSNE function requires this type of distance matrix input, and the linkage function for hierarchical agglomerative clustering requires this flattened distance matrix input. Okay, and so basically, once we've created that distance matrix in flattened form, every other line of code is exactly the same as what we've seen before. So we still put that distance matrix into our linkage function, specifying the linkage function that we like to use, so like single linkage. Okay, that creates this object here. Okay, and if we want to visualize the single linkage dendrogram, we can use the dendrogram function like we've done before. Okay, and I'm specifying a few additional parameters here that we haven't seen before. So one additional thing that I'm going to specify is the following set of parameters. So if you're ever faced with a situation in which you have a ton of observations in your data set that you just clustered, it becomes quite messy to basically visualize every single one of those observations on your, or basically at the bottom of the tree. So if there's too many observations such that you don't want your tree to look really messy, what you can do is basically you can specify that, number one, don't show me any labels. But then number two, you can implement this truncate mode here, which basically cuts off, basically it only shows you the final 200 merges that end up happening in the hierarchical agglomerative clustering algorithm. So we specified 200 right here. So we call this the truncate mode. Now, because of that, what this means is that it's technically possible that this little blue line here does not actually correspond to just one observation. It's possible that perhaps more merges might have happened further on down the tree. So something like that, such that this, one of these lines might actually correspond to like multiple sets of observations. So by truncating, you don't quite know, how many observations a given child node at the bottom of the tree corresponds to. But sometimes we have to do this in order to actually visualize, what's going on with the final merges. Sorry about that. So, yeah, man. Okay, so this is how we would create there's other questions that I wanted to go over, but we'll have to skip over that. So this is how we create a single linkage clustering with our categorical data set. And much like we saw with, using hierarchical agglomerative clusterings with purely numerical data sets, we can also extract just a single clustering from that dendrogram. So let's just say, for instance, I wanted to, one at a time, extract the dendrogram clusterings with 2, 3, 4, all the way up to 12 clusters. So again, I can use that agglomerative clustering function, but what I want to focus on here, so there's a key distinction that I'm using now. So if I don't plan on using the Euclidean distance matrix, right, then I actually do need to specify that I am going to be bringing in my own pre-computed distance matrix. So if my original data set was comprised of numerical variables, then I would simply just put that numerical variable data set here. Okay, but because I want to bring in my own distance matrix, i.e. the Hamming distance matrix that I've created, I need to pre-specify that here. Okay, and so I also need to specify the linkage function that I like. Okay, and so what I can in fact see now is basically a color coding of each of my clusterings in that single linkage dendrogram with so basically I'm visualizing the clustering with 2 clusters, the clustering with 3 clusters, so on and so forth. And so basically what we can see here is that the single linkage dendrogram is showing us a pattern that we often see in the single linkage dendrogram when we're dealing with numerical data sets, right? So the notion of an outlier for categorical variable data sets is slightly different than the notion of an outlier for numerical variable data sets. But what we do end up seeing here is that the dendrogram is in fact picking off one at a time these points that don't have a lot in common with any other point in the data set, or they don't have as much in common with any other point in the data set. And so we can see that here in the dendrogram as well, right? So for instance, the final few sets of observations that were merged last are these observations here, which we can't necessarily see are leading to singleton observations, but we actually verified here in our TS&E plots that the clusters that were getting picked off were in fact these singleton clusters that did not have a lot in common with the other observations. Okay, so I ran out of time, but very quickly, you can basically do this. You can basically create a dendrogram using complete linkage as well as average linkage as well. The only thing that would really change is, now you're using complete linkage here. So you've created a complete linkage dendrogram using the Hamming distance as your original distance metric. And you can color code the observations here. And then we can also do the same thing with average linkage. So this is our average linkage dendrogram constructed on our categorical data set using the Hamming distance instead. And what we can also do is color code each of our clusterings from that dendrogram in the TS&E plot for further inspection. So for instance, very quickly, we can see that, the average linkage clustering that had 9 clusters actually does produce this clustering that has a relatively high degree of an association with the TS&E plot suggested clusters. Or in other words, the difference between cluster 3 and cluster 1, we do actually have evidence to suggest there is this meaningful separation that exists between those points. However, the downside is that basically in order to get to this clustering, we had to pick off a bunch of very small clusters from the larger main clusters that we might be wanting to get. So there's pros and cons to all of these dendrograms that we've created here, essentially. Okay, sorry about that. So I went over time, so I will stop recording.